So hello everyone for the welcome to the presentation of machine learning with Python. And today's session is going to be carried out on linear regression. So let's get started. First, what are the goals of this session and what we'll be learning today? So after this session, in this session we'll be discussing the concept of simple and multiple linear regression and its application in predictive analytics, build simple linear and multiple linear regression models using Python package stats model. And while doing so, we'll be learning few of the basic things while training a model, which is to predict the data set into training and validation data, then building the regression model using the Python package on training data set and test on the validation data set. Then learn how to incorporate categorical or called as qualitative variables in a regression model. Then learn regression model diagnostics and perform tasks such as residual analysis, identification of outliers, and influential observations. So let's get started with simple linear regression first. So it's a statistical technique used for finding the existence of an association relationship between a dependent variable and an independent variable. Dependent variable, also known as a response variable or outcome variable, and independent variable, also known as an explanatory variable and or predictor variable or feature. Now, in simple linear regression, what we are trying to do is there is one variable and we are trying to predict the outcome of that variable with its effect. So what in simple linear regression we are doing is there is a cause and there is an effect to that cause. So our cause are the independent variables and effects are the dependent variables. So examples of simple linear regression are soil erosion, rainfall, where soil erosion being the independent, rainfall being the independent variable, soil erosion being the dependent variable, then work experience and the salary of the person. The work experiences being the independent variable and the salary being the dependent variable. Then vehicle's age and the vehicle's resale value. The vehicle's age being the independent one and the dependent one being the vehicle's resale value. So some of the other examples for simple and multiple linear regression are a hospital interested in finding out the total cost of a patient for treatment varies with the body weight of the patient. So the treatment and the body weight of the patient. Then insurance companies trying to understand the association between the healthcare costs and aging. An organization interested in finding the relationship between the revenue generated from product and features such as the price, money spent on promotion, competitors' price, and promotion expenses. The restaurants trying to know the relationship between the customer's waiting time after placing the order and the revenue. An e-commerce platform trying to get the features and understand the number of clicks, visits, customer visits to their portal, then clicks on the product, number of items on sale, average discount percentage, and their effects, and how they contribute to their revenue. Then banks and other financial institutions are trying to understand the impact of variables such as unemployment rate, marital status, balance in the bank book, bank account, rainfall, etc. On the percentage of non-performing assets, the NPAs. So after understanding what is a simple linear regression, we'll start building a regression model. And first, before building, we'll discuss the steps of building a model. So first, the step one is obviously to collect the data. So uh, to collect the data on a dependent variable and independent variables from different data sources, and which can also be time consuming and can take uh, almost 70 to 80% of the time, the data related tasks. And as you can see, the second point also mentioning, even when the enterprise resource planning system is available to a company, it can be still time consuming. Then pre-processing the data. Before the model is built, it is essential to ensure the quality of the data for issues such as reliability, completeness, usefulness, accuracy, missing data, and outliers. The data imputation technique may be used to deal with missing data. Use of descriptive analysis and visualizations may be used to identify the existence of outliers and variability in the dataset. Then new variables can be derived and used in the modeling, which is also known as feature engineering. Then categorical data uh, has to be pre-processed using dummy variables before it is used in the regression model, which we'll see in the further example. Then splitting the data into the training and testing sets, which is in a normal terms, it is done in an 80-20 for training and testing respectively. So training set is the set from which the model will learn the data and learn the task of predicting from it. The type of the training data usually determines the ability of the model to generalize. That is, the better the quality and diversity of the training data, the better will be the performance of the model. This data is of the model. So as I mentioned, it is taken around 80% of the whole data set for training. So it can be 60-40, 70-30, or 80-20. Then testing a set. After once the model has been trained on the training data or the training set, the testing set is used in order to evaluate the performance of the model. Once it has been nicely trained on the training set, the validation and the testing set are usually combined and is used as the testing set, which is not considered a good practice. But if so it is better to use a separate validation set as well. And the accuracy of the model on training data is greater than on the testing data, then the model is said to have overfitting. Or in general terms, if you say overfitting, it means that it has understood only the set that it has been trained on, and it does not generalize the data very well. So this data is approximately 20 to 25% of the total data available for the project, as said for the 80-20 split. Then the validation set. The validation set is used to fine-tune the hyperparameters of the model and is considered a part of the training of the model. The validation. The model only sees this data for evaluation but does not learn from this data, providing an objective, unbiased evaluation of the model. Validation dataset can be utilized for regression as well by interrupting training of model when loss of validation data set becomes greater than the loss of training data set. That is reducing bias and variance. This data is approximately 10 to 15% of the total data available for the project, but this can change depending on the number of hyperparameters. So if the model has quite many hyperparameters, then using large validation set will give better results. However, whenever the accuracy of the model on validation set is greater than that of the training data, then the model is said to have generalized well. Then the performing descriptive analytics or data exploration. The descriptive statistics will help us to understand the variability in the model and visualization of the data through techniques like box plot for showing the outliers or scatter plot for displaying displaying the obvious relationships between the two variables in consideration, and also useful to describe the functional relationship between the dependent or outcome variable and features. Then building the model. The model is built using the training data set to estimate the regression parameters. The method of ordinary least squares, which is OLS, is used to estimate the regression parameters. Ordinary least squares is a technique used in linear regression model to find the best fitting line for a set of data points by minimizing the residuals, the differences between the observed and the predicted values, the residuals. Then perform model diagnostics. The regression is often misused since many times the model fails to perform necessary diagnostic tests before applying the model. Before it can be applied, it is necessary that the model created is validated for all model assumptions, including the definition of the function form. If the model assumptions are violated, then the modeler must use remedial measures. The functional form is something that we'll be discussing for the multiple linear regression further. Then validate the model and measure model accuracy. A major concern in the analytics is overfitting, as also mentioned before. It is important to ensure that the model performance is consistent on the validation dataset as is in the training dataset. In fact, the model may be cross-validated using multiple training and test datasets in order to get a good measure of model's accuracy. Using multiple test data and training data helps the model to get accustomed to the various data changes and have more better insights into the generalization of the data. Then decide on model development. The final step in the regression model is to develop a deployment strategy in the form of actionable items and business rules that can be used by the organization. This is nothing but the business logic that comes in alignment with the development of the model. So let's start building the simple linear regression model. First, we'll discuss some of the mathematics related to the linear regression, simple linear regression. Mathematically speaking, it can be the relation between the independent variable x can, for finding the output y, can be represented as this, which is y equals to beta 0 plus beta 1 x plus epsilon. So y is the outcome or the predicted value or the dependent variable beta 0 is the intercept, beta 1 is the regression coefficient, and x is the independent variable, and epsilon is the error of the estimate. So for the data set of n observations, or our mathematical representation would look something like yi, the one that is showed, which is yi equals to beta 0 plus beta 1 xi plus epsilon I. So continuing the discussion further for the mathematical representation on the data set for the simple linear regression. The epsilon is added because the regression relationship stated in equation is a statistical relationship. So so it is not exact, unlike a mathematical relationship. So the regression parameters beta 0 and beta 1 are estimated by minimizing the sum of squared errors, SSE. And you can see the beta 1 estimation equals to summation of from I equals to 1 to n goes for xi minus x bar into yi minus y bar divided by xi minus x bar whole square. And for estimation of beta 0 is a y bar minus beta 1 x bar. So as you can see, the beta 0 and beta 1 are the estimated values for the regression parameters beta 0 and beta 1. Actually, beta 1 and beta 0 cap. So, or hat. So the coefficients are estimated using methods such as ordinary least squares, also mentioned before, which minimizes the sum of squared differences between the observed values and the values predicted by the linear model. So the estimate using the OLS gives the best linear unbiased estimates, which can also be said true of the regression parameter. So there are certain underlying assumptions when we work with linear regression models that we have to keep in mind. First is linearity. The relationship between the dependent and the independent variable is linear. Then independence, the errors or the epsilon that was mentioned in the mathematical representation, the errors are independent. Then homoscedasticity, which is the constant variance. The residuals have the constant variance, and if the residuals don't have the constant variance, or it's a non-constant variance, it is called heteroscedasticity. Then normality, the residuals of the model are normally distributed. The the then let's discuss some of the properties of let's discuss the properties of the simple linear regression. The mean value of yi for given xi is for yi for given x is beta 0 hat plus beta 1 hat x. Then yi follows a normal distribution with mean. So beta 0 hat plus beta 1 hat x, and variance for epsilon. So let's start understanding it with the help of an example. So what we are trying to do here is we are taking some MBA grads, 50 MBA grad students, and predicting their salary based on their percentage that these students received in grade 10. So what we are trying to do is we are trying to develop a simple linear regression model to understand and predict the salary based on the percentage of the marks that these MBA grad 50 MBA grad students got in the grade 10. So if we uh, look at some of the data or the top 10 entries in the data, it would look something like what has been displayed on the screen right now. Then steps for building a regression model using Python. We'll use the pandas and NumPy libraries. Then read the data set into the data frame. Then identify the features X, which is the independent variable, and the outcome variable Y, which is also known as dependent variable in the data frame for building the model. Then fourth is split the dataset into training and the training test and validation sets using the train test split. Then import stats model library and fit the model using the OLS method, ordinary least squares method. Then print the model summary and conduct the model diagnostics. So let's get started. So first I'll display what we'll be doing here on the screen and then on the Jupyter book. So Jupyter notebook. So first, as discussed, we'll be importing the. We'll see the Python code here. I'll try to keep a screenshot of the result and then show you on the notebook live. So first, we'll start with the importing the important libraries, which are pandas and NumPy. Then reading the reading the data set, which is MBA salary.csv. CSV is nothing but the comma separated value, and then printing their top 10 entries in the data set. And if we want to have an info on the data set, then you can see the how we can print it and what on the screenshot of it. You can see the things like memory usage, the columns, number of entries and stuff. So the memory usage is 1.3 KB. And also the data types. The data types are especially important when dealing with certain methods which does not support certain data types in their application for simple to many different reasons. So creating the feature set and the outcome variable. So if we take a reference to the mathematical representation of it, the X, the percentage in tenth, and Y is the salary, and the OLS method will be used. So we'll be using the stat models API in order to use the OLS method, and which will be taking the two parameters of X and Y. The beta 0 is a 1 here, and will be added as a separate column as mentioned. So before moving to the splitting, this is just an excerpt used from the scikit-learn's page itself. So for displaying the various parameters that they uh, uh, they provide. So starting with the arrays, which are sequence of indexables with the same length or shape 0, then uh, you can see the allowed inputs, which are list, numpy arrays, then scipy sparse, matrices, and pandas data frames. And then the test size, as you remember, the testing and the train. So which will be 0.80 and 20, 0.20 and 80 for test and train respectively. Then random state. Random state is nothing but and, it it is it is the random state is generally used in order to keep uh, keep a data set fixed by giving it a number, and then trying to reproduce it just in case if we want to have the same results or follow the same kind of state of the data set. The shuffle is another bool value. Uh, so it says whether or not to shuffle the data before splitting. Then stratify. If not, none. Data is splitted into the stratified fashion using this as the class labels. So so we'll be splitting the data set into training and validation sets. The train test split method will be used, which will return the 4 variables, which are train x, train y, test x, and test y. Train x containing the features of the training set, train y containing the values of response variables for the training set. Test x contains the x features of the test set, and test y contains the values of the response variable for the test set. So below is a uh, Python code that will be used uh, for the train and test of it, and the split. You can see the train size, which is 0.8, which is 80% and 20% for the validation of the model. Then using the OLS method in order to fit the model, which will return the so the OLS estimates the parameters and returns the model information to the variable MBA salary that we will be creating, which will be containing the model parameters, accuracy measures, and the residual values, among other details. So printing the estimated parameters and interpreting them. So for the MBA salary LM, which was the variable that we created, the parameters will be, you can see the output of it. So the estimated model or the predicted can be returned for the MBA salary in in different forms, which is nothing but the mathematical representation of it. So the MBA salary equals to 30587.285 plus 3560.587 multiplied by the percentage in grade 10 is nothing but the representation of the functional value that we have presented for the simple linear regression. So for every 1% increase in the grade 10, the salary of the MBA students will increase by 3560.587. So this is the value of the beta 1, and that is what the regression coefficients does. It helps us to understand for a 1 unit increase how much it will affect the value or the outcome of y. So 1 unit increase in the independent variable, how much it will affect the value of the outcome or the y variable. So we'll recap what we have seen in the slides here. Just a second, let me check if it's visible on the screen or not. So let's so starting with the importing the necessary libraries, reading the file, then identifying the features and the outcome variable, splitting the set into the data and into the training and the validation set. Then using the stats model library for fitting the model using the OLS, and printing the model summary. This was something that we also discussed in the slides. So, and so for example, as you remember, start we started with we took the example of MBA grads, and using their grades in grade 10th, we are trying to predict their salary after the graduation. So importing the necessary libraries and setting the print options of precision one, and this is nothing but the decimal value, and and the line width for 100. Then reading the CSV file and printing their top 10 entries or observations. And then we use the info in order to get the information about the data set. So you can see the number of entries, the number of columns, the data types that are there in the columns, that are used in the columns, and the memory usage of it. Then creating the X and Y feature. So we'll be using the stats model API and using their OLS method for fitting the model. So this constant is nothing but the beta 0 value. Then the Y as keeping the Y as salary. Training splitting the for train test split for the splitting the train and the test data set. Then fitting the model here. Then printing the estimated parameters and interpreting them. So you can see the parameters here, and this is the value of the beta 1 that we got. So for so this was the regression coefficients value. So for every 1 unit of increase in x will give us this much increase in the, and this will be the coefficient change that will be in outcome of the y. So now model diagnostics, which is used for checking or validating the model before putting it into the practical use. The following measures are used to validate the simple linear regression models, which are coefficient of determination, R squared, and hypothesis test for the regression coefficient, analysis of variance for overall model validity, important for the multiple linear regression models. Then residual analysis to validate the regression assumptions. The assumptions that we discussed at the beginning of discussing the simple linear regression model. Then outlier analysis, since the presence of outliers can significantly impact the regression parameters. So the coefficient of determination, which is also known as R squared. So you can see the mathematical representation of it. The y equals to beta 0 plus beta 1 into xi plus estimation of the errors epsilon I. So the variations in y explained by the model, and the variation in y not explained by the models are the estimation of the errors. So for that, we'll be using the estimation of yi values, which is yi hat equals to beta 0 hat plus beta 1 hat xi, where the SST, which is the sum of squares of total variation, the SSR, sum of squares of explained variation due to the regression model, and the sum of squares of the unexplained variation, which is the error. And you can see the correlation of them with for summation of summation starting from I to n. We have y minus y bar whole square for SST, and which is equals to the summation of y hat minus y bar whole square plus a summation of I equals to 1 to n y minus y hat whole square for SSE. So just for the reference, SST is sum of square of total variation. SSR is sum of square of explained variation due to the regression models, and the SSE for sum of squares of errors. So the coefficient of the determination R squared is given by the SSR divided by SST, which is also equals to 1 minus SSE divided by SST. The properties for the R squared are given as follows. The value of R squared lies between 0 and 1, and the R squared is a square of correlation coefficient, where R is the Pearson correlation coefficient. Higher R squared indicates a better fit. However, one should be careful about the spurious relationship. So the hypothesis testing for the regression coefficient. So if we take the beta 1 equals to 0, we can conclude that there is no statistically significant linear relationship between the two variables. So Hypothesis testing is as you remember, we hold a hypothesis which is a null hypothesis and an alternate hypothesis. Null hypothesis represented by H0, which is represented over here. Then the alternate hypothesis is beta 1 is not being equal to 0, whereas our null hypothesis, the present or the current belief based on whatever data that we had, say beta 1 equals to 0. So the corresponding test statistic of the hypothesis is given by the uh, the equation T of alpha divided by 2 and n minus 1 equals to beta 1 hat divided by standard error of beta 1 hat. So the standard error of estimate of the regression coefficient is given by the standard error estimate of beta 1 hat equals to SE divided by the square root of xi minus x bar whole square. Just for the sake of a simple explanation, the beta 1 hat is just interpreted while typing and is shifted somewhat to the right. So not to be confused with the power symbol for the beta hat. So SE being the standard error of the estimated value of yi, and the residuals and is given by the formula SE equals to square root of yi minus yi hat divided by n minus 2. So the hypothesis test is a two-tailed test. The test statistic is given by the equation as mentioned before. It's a t distribution with n minus 2 degrees of freedom. The 2 degrees of freedom are lost due to the estimation of the two regression parameters, beta 0 and beta 1. So SE is nothing. SE beta 1 hat is nothing but the standard error of regression coefficient beta 1 hat. So the analysis of variance in regression analysis. So we have multiple beliefs, and we of them being equal. So this is our null hypothesis where B1 equals to B2 till Bk is all equals to 0. And the alternate hypothesis is states that not all the regression coefficients are 0. So some can be, some cannot be. So the corresponding F statistic is given by F equals to MSR divided by MSE, where SSR divided by K divided by SSE and divided by N minus K minus 1. Where MSR as mentioned in the formula is nothing but the mean squared regression, and the MSE is also mentioned before for the mean squared error. The F test is used for calculating whether the overall regression model is statistically significant or not. So if we get to the summary of the model that we have created and printed, so this is what the summary would look like for it, for the model that was created. You can see the OLS model, the dependent variable being salary, the number of observations, then the R squared value. We'll be discussing the R squared value again further. The the coefficient, standard error, the p value and stuff, and the Durbin-Watson value, where its value is 2.61, which is around 2. But Durbin-Watson will be important in the multiple linear regression further. So based on the output that we have printed or the summary, the R-squared value of the model is 0.21. The model accounts for the 21.1% of the variation in salary. Then the p-value for the t-test is 0.0029, indicating a statistically significant relationship between the percentage in grade 10 and the salary. And for that t statistics, we have taken the value of alpha as 0.05, which is normally taken. If the task is less severe, then we can also go for a 0.1 value for the alpha. The probability value for the F statistics of the model is also 0.0029, demonstrating that the overall model is statistically significant. It's important to note that in simple linear regression, the p-values for the t-test and the f-test are the same because they test the same null hypothesis. So additionally, in the case of a simple linear regression, the f statistic equals the square of the t statistics. So f equals to t square. Stating in that manner. Then moving further on the model diagnostics, the residual analysis. So errors are also called as residuals, which is represented by y minus y hat. So residual analysis is also known as salvage value assessment, which is used to evaluate a linear regression model's performance by analyzing the residuals. It helps identify and rectify model issues, assess assumptions, and detect outliers for the improved efficiency. It is performed to check the following, which is the residuals are normally distributed, variance of residual is constant, which is homoscedasticity. The functional form of regression is correctly specified, and there are no outliers. So, as discussed here, the residuals follow a normal distribution. So we'll check the normal distribution for residuals with the help of a probability plot, which is PP plot. So the probability plot compares the cumulative distribution function of two probability distributions against each other. Using the prop plot method on stat model to draw the plot, we'll draw the plot of the probability plot. So if so this is what the libraries that were needed and the Python code. You can see the MBA salary resid, which is a residual used for this. The prop plot for plotting the values. The PP plot line 45 is nothing but the angle given, and the plot title, and plot show to make sure that it shows up. uh, it is being displayed. So you can see the interpretation of the plot, as you can see in the image, can be easily done, as most of the, so the line represents the cumulative distribution of a normal distribution, and the date and the dots are nothing but the residuals, which are approximately around the line. So so now testing for the homoscedasticity, which is a which basically means having a constant variance. So starting with point number 2, to observe the homoscedasticity by drawing a residual plot, a plot between the standardized residual value, standardized predicted value, a custom function called get standardized values will be used, and a formula for it will be applied over there. So you can see the function that was created and the values it returns. Values minus mean of that, or y minus y bar by uh, stand, uh, the standard value. So why do we use the standardized value first? This method transforms the original values into a standardized scale with a mean of 0 and a standard deviation of 1, facilitating better comparison, interpretation of coefficients, numerical stability, and adherence to the regression assumptions. So you can see the plot that we have on the left. The plot, you can see the it's uh, not making any shape in a way, as compared to the shape that it is making on the image on the right. The funnel type shape of the residuals, uh, sorry, the the points will be indicating the presence of heteroscedasticity, whereas on which is not present on the left side of the image. Now, detecting the outliers. First of all, what are outliers first? Outliers are values that are at extreme ends of the dataset. Some outliers represent true values from the natural variation in the population. Other outliers may result in incorrect data entry, equipment malfunctions, or other measurement errors that can be caused while entering the data or making the data, or collecting the data. So an outlier isn't always a form of dirty or incorrect data. So you have to be careful with them in data cleansing. What should uh, what should be done with an outlier depends on what most likely causes the outlier to happen. So the true outliers should always be retained in your dataset, because these just represent the natural variations that are present in the sample. So outlier analysis is a crucial step in data mining that focuses on identifying abnormal or rare items within a dataset. These outliers significantly deviate from the majority of the data points and can sometimes indicate problems, errors, or conditions that warrant further investigations. So, as also mentioned before, what they show is a large deviation from the mean values, and the outliers presence can significantly influence the regression coefficients. So, for For measuring the uh, influence of the influential observations, there are different techniques. Some of them are z-score, Mahalanobis distance, the Cook's distance, and the leverage values. So starting with the set score, it's a standardized measure that indicates how many standard deviations a data point is from the mean. It is calculated by subtracting the mean from the data and dividing by the standard deviation. The set score are useful for identifying univariate outliers, but do not account for the multivariate relationships. Then the Cook's distance is a measure of influence of the data point on the overall regression model. It combines information about the residual and the leverage of a point. Cook's distance quantifies how much the regression coefficients would change if a particular data point was removed from the analysis. So points with a large Cook's distance are considered influential. So if the Cook's distance, denoted as t, is higher than 1 or 2 times the square root of k by n, where k are the number of coefficients and the n is the sample size, the observation is likely to be influential. A common threshold is b being greater than 1 for identifying the highly influential points. Then first, before going to the Mahalanobis distance, we'll discuss the leverage values first, which are just observation measures the influence of the observation on the overall fit of the regression function and is related to the Mahalanobis distance. So the leverage values of more than 3k plus 1 divided by n is treated as a highly influential observation, where k is the number of features in the model and n is the sample size, just as before. So, and coming to the Mahalanobis distance, it is a multivariate distance measure that rescales variables based on their eigenvectors to remove correlations between their variables. It measures the distance of the data point from the mean of the data in the multidimensional space, taking into account the covariance structure of the data. Points with a large Mahalanobis distance may be multivariate outliers. So to summarize, z-score identifies the univariate outliers, Mahalanobis identifies the multivariate outliers, Cook's distance measures the overall influence on the regression model, and the leverage values assesses the influence on predicted values. And these measures can be used to identify the influential observations that may unduly affect the results of a statistical analysis. So for if running the z-score for our data set, we have found that there are no values for it, and it will show the very image that screenshot that has been displayed on the screen. And we are displaying the z-score value greater than 3, by the way, as you can see in the code. Then the then the Cook's distance. You can see the code. And you can see the largest Cook's distance that is been given by the row index 15. But none of them are exceeding more than 1. then the leverage values, and plotting them in a scatter plot. Uh, uh, so uh, uh, for the uh, for the leverage value versus the residuals graph, so you can see the 13, 8, and 15 being uh, away from the normal distribution of it. So the size of the circle is proportional to the product of residual and leverage value. Larger the circle, larger is the residual, and hence the influence of the observation. Making the prediction and measuring the accuracy of the model. So how our model performs on making predictions on the test and validation dataset and measuring its accuracy. Predicting predicting using the validation set. The model variable has a method predict, which takes the x parameter and returns the predicted values. So we'll create a pred y for MBA salary ln and predict the test x, and giving it the argument test x for predict method. So for this, the MSE, or the mean square error, the root mean square error, and the mean absolute percentage error are used frequently for these measures. The testing the accuracy of the predicted value will be using the R2 score and the mean squared error for measuring the R squared and the MSE values. So R2 score, also known as the coefficient of determination, evaluates the performance of the regression model. It quantifies the proportion of variance in the dependent variable that can be explained by the independent variable. So the formula is of the R2 score is calculated as R2 equals to 1 minus uh, the sum of squares of the residual errors divided by the sum of squares of total sum of squares, or the sum of squares of all the squares. So interpretation of the R2 square for 0.68, as you can see, is being indicates 68% of the variability dependent output attribute can be explained by the model, while the remaining 32% is unaccounted for. So a higher R2 score is desirable, and it signifies a better fit for of the model to the data. The range of the R2 is from 0 to 1, 1 indicating a perfectly fit model fit predicts the dependent variable, while a score of 0 means it does not explain any variability in the dependent variable, better than the simply predicting the mean of the dependent variable. Then usage is R2 score is commonly used in regression analysis to assess how well the model fits the data. It helps in comparing different models and understanding the proportion of variance explained by the model. So as mentioned, R2 score and the mean squared error will be used. So these are the two methods we'll be using to predict the Y values and the actual Y values to calculate the accuracy measures. So for the mean squared error, the root mean squared error will be needed, for which we'll be using the NumPy module, which has the square root method in it. So an R2 of 0.1 156 indicates the model only accounts for the 15.6% of the variation in the validation set, suggesting poor fit and predictive performance. The root mean squared error value of 73458.04 represents the average error the model makes in predicting the outcome. It is in the same unit as the target variable. The smaller the root mean squared error indicates better performance, as it suggests the model is making small errors, actual errors on the average. An RSME of 0 would indicate a perfect prediction accuracy. Now, calculating the prediction intervals. Now we have been predicting the value, but sometimes if we need to predict in which interval the particular observation will fall in. So for the this is done with the help of with the help of a probability being used in it, and as if we are using probability, if we'll be using an alpha value or the significance level. So here, as you can see, we are using an alpha value of 0.1, which gives us the confidence interval of a 90%. We'll be using the WS predictions STD method, which will return the prediction interval while making a prediction as well. So this is a these are the important libraries that we'll be using. So including them, using the sklearn model selection to train a test bed for the train test bed. These are nothing but some of them being combined into one that we have seen before. Now for the model diagnostics, for the model diagnostics, starting with the test of homoscedasticity. This is the formula that we have followed, and that will be returned. Then moving further with that, we also used a scatter plot for the MBA salary prediction, the predicted values, and the for the residuals. Then the outlier analysis was used. Outlier analysis. We discussed Z-score method, then leverage values, etc. So for that, we'll be using the SciPy and import Z-score. The Z-score passed for the MBA salary DF that and the salary we created a DF for that. And as you also remember for the slide, I showed the screenshot of it. For that, according to the Z-score, there are no values yet. Then for the Cook's distance, this was the code for it, and you can see that none of the Cook's distance are passing the value of 1 over here. Then the leverage values showing the observations as well as the circles, and larger the circles and larger the influence on them. So the 13, 15, 8 and 15 were the one that were showcased on the slides as well for the influence. Now moving for the prediction of the prediction on the validation set. So we create a pred y for the prediction and passing the test x. So using the R2 square, now testing the accuracy of the predicted values. So testing the using the R2 square and the mean squared error. So for R2 square, we are getting the 15.5, 15.6% of the variation in the validation set. Suggesting a poor fit and predictive performance. Then the mean squared error of 73458.04. Now calculating the prediction interval. This was the code that was also mentioned in on the slide using the pred-y. Then predicting the low and high interval values of the y. With alpha's value as 0.1 as a 90% confidence interval is used. And you can see the values of them being from 0 to 10, the values of them being listed over here. So this was it for the simple linear regression model. And just a second.